We did one like this in class too. So, no, you have to read it off the board.
When have I been nice?
There you go. All right, so in this one, you're trying to figure out, you want the probability that you've got the S squared in between two values is 0.9. 0.9? Okay. All right, so the idea is that I don't know the distribution of S squared by itself, but I do know that if I do n minus 1 S squared over sigma squared, what is that? Of n minus 1, right? Okay. So if I work inside here and multiply this like so, I can figure out values for this to work, right? If I, sorry, go ahead.
You're using the n from the first part where n is 25.
Yes. And you're going to use the sigma squared, that's the 12.3 squared.
Mm-hmm. And that's the, so it's going to divide by 12.3 squared instead of just 12.3.
Yes. Yes, because that's what they tell you the variance is.
What problem was
9, yeah. 9 part C, 5.5-9 part C. But so this, this one you can read from the table. Because I think there's only two things in the table that will subtract and give you 0.9. Like we had an example like that in class, right? Yeah, you pick those two values out, and then you'll have to solve for A and B from there. Because you'll know that whatever the 24A over the variance will have to equal that left number, and 24B over the variance will have to equal the right number. And so you solve for A and B.
So you're going to plug in like whatever number you get for A, and then the other side for.
You're going to set it equal to that number that you get and solve for A and B. You don't want to plug them in for A and B. The reason for that is if you've got that chi-squared random variable in the middle, right? I'm going to pick, I think you picked the 0.95 for that one and the 0.05 for that one. If I remember, that's the values that you can actually subtract to get 0.9. It's those pieces that'll be the bounds. So you'll have to solve for the A and B. You don't want to plug them in for the A and B.
Okay.
Because the values that you're getting out of the table are the bounds. They are the leftmost and the rightmost numbers that you're going to use.
Mm-hmm. Okay, and you're using row 24?
Yeah, that's right. Yeah. Do you have a question, Sam?
Yeah. For the worksheet you handed out, for the first one, it says use 2 methods for estimating. What do we do for the first method?
It says unbiased sample variance, right?
Yeah.
So that's when you do the 1 over n minus 1 times the sum of the. Yeah.
What? The like long version of it?
Yeah, you use this formula. Yeah. That's what it's asking you to do. Which I think is the same thing as, if I remember correctly. If you go through and simplify it, you get that. Of course, the really easy way is just to plug it into a calculator or Excel and tell it to tell you what it is. Yeah. If you tell me where you got it from. It's only 5, so it's not that hard to do, but I expect you to use the technology to do it. I did. I didn't care. I just wanted a good game.
What's your expectations?
I would say the end of the first half really, really irritated me. Let's not call a timeout. Let the clock run. And then, we're on defense, and they decided they were going to run out the clock. And so I'm not going to call a timeout. So we're just going to have bad coaching on both sides. Yeah, that was really fun.
Did you enjoy the halftime show?
I didn't watch the halftime show.
Did you?
Who was doing it?
I liked it.
It's fine if you like it. I went down and made dinner. That was dinner break.
I love J-Lo. Right?
I've never watched that
And then you're always
halftime show.
singing that also recording.
They're getting worse. This one was better than last year.
Oh, that's good.
That was her daughter. She sang with her.
Yeah. Other questions? Or did that answer your question? Okay, what else do you have a question about? Oh, okay.
The 14 one, when it said approximate with the Poisson approximation, but they don't give us the lambda.
Where are we looking? Sorry.
Sorry, on page 267, number 14.
Oh, when it says plus, yeah, so you can figure out the lambda. What's the mean of the binomial? Mm-hmm. Okay, so that's what you use for lambda.
So you just, okay. So like we did the normal, like we used those numbers for a normal.
Mm-hmm.
I see.
Yeah, but it's the same idea.
Okay.
Yeah, Sam.
Why do we use brackets instead of parentheses? Confidence.
Does it matter?
I guess it did.
The book, I don't know. The book just chooses to use that, but again, for continuous distributions, it really doesn't matter. The probability you actually get that is 0. So, I think it's just a matter of preference of how you write it. I've seen other books use parentheses, so I don't think it matters.
So do you do the integer correction when you're doing approximating things?
You do the integer correction when you use a continuous distribution to approximate the discrete.
Okay.
That's the idea. Yeah.
Dr. Joe, actually, I'm very disappointed in your schedule this semester because I can never talk to you on Monday.
I'm sorry. What did I do?
It has nothing to do with you. It's just when you're in class is the only time that I have in my day.
I'm here at 8.
But I'm not gonna say.
Well, there you go.
I was like, I'm gonna get up at 9 to go see Dr. Joe, and I was like,
Yeah, Dr. Joe's in class. Sorry.
are you in the office all day Tuesday?
Mm-hmm. I'm here at 8. I'll be here all day tomorrow. I meet with Grace and some others at 8:30, but
Yeah.
any other questions before we get going?
Oh, I do have one question.
Okay.
When did they pick the president? The new president?
When did they?
When are they?
When are they? From what I understand, they're supposed to make a decision this week and make an offer, but I have no idea when the official announcement thing will come out.
I thought it was on the same date as you.
He's talking about the university president.
Oh, I thought we were talking about the president, and I was like,
That's imagining now.
hey, you didn't specify university.
It was pretty obvious from what he said.
Okay, but it was a little
fair because they've been talking about the.
I mean, not really. I'm trying to make it.
You're trying to stand up for Grace. It's just not working.
Not working.
Other questions? We're good now? All right, I want to look at number 15. This is on page 282. They tell you that the x1 out to xn is a random sample from the interval theta minus 1, oops, from a distribution, I forgot. That is uniform on theta minus 1, theta plus 1. So the first part says find a moment of, and that's really what I care about, and then I'll talk about the part C, but it asks you to find the method of moments estimator for theta. That's a U.
Oh.
It's uniform.
I didn't hear you say it.
All right, so we talked about this at the end of class we talked about the idea of method of moments at the end of class last time, right? Okay. So how many parameters are we trying to get estimators for? 1. So how many moments are we going to need? 1, right? So then what moment are we going to use here? The first, good. So what do we set equal to our first moment based on our sample? This would be the expected value of x bar, yeah. Yeah, that's what the mean is, correct? We want to set it equal to the mean of the distribution, which in this case is what? I didn't want to write it that way. I don't want to write it that way, sorry. I want to write this as 1 over n sum of x of I, right? That's our first moment. What is the mean going to be here, sorry? How do you find the mean?
1 over theta plus 1 minus theta.
That's the PDF.
Oh, I'm stupid.
Is it B minus A? Ah, B plus A over 2.
Wow.
Yeah. Yeah, it's just theta.
So 2 theta.
Yeah. No, 2 theta over 2, right? Here. This will be your theta hat. Well, I guess we'll use a hat. It's fine. That'll be our estimator. Okay, cool. Good. Phew. All right.
We got there.
We did get there. It's true. So in this case, the method of moments estimator is the sample mean. Okay, so part B gives you a set of 5 data points and asks you to figure out the estimator. Well, you just take the average of the 5 points. So that's not that big of a deal. So that's it. But the idea behind this is we set the sample mean, our little x bar, equal to what the mean of the distribution is and solve. In this case, the mean of the distribution turned out to be exactly what we were looking for. So there wasn't any solving really to do. Right? Okay. What the book mentions as well, and I'm not going to do much work with this, is that this is not the maximum likelihood estimator. We saw the one before where we did the uniform on 0 to theta, and our maximum likelihood estimator was the maximum of the x of i's. Right? When we did the uniform from 0 to theta, when we did the maximum likelihood estimator, we got the maximum. We used the maximum as the maximum likelihood estimator. A similar thing happens here. The maximum likelihood estimator for theta in this case is not the mean. It's actually, you take the maximum plus the minimum and divide it by 2. It kind of looks like the mean, but this is how you would do the maximum likelihood estimator. You would get that from, you have to do a little bit more of an explanation more than there is any work to do. Because what is your PDF for this uniform distribution? How do you find the PDF for a uniform? It's 1 over B minus A, right? When I do B minus A, I get 2. I don't get theta. So your likelihood function would just be 1 over 2 to the n when I multiply it together. But when we differentiate with respect to theta, you would just get 0. Right? So when you do your math, so you have to, so it doesn't matter what you pick for your x's. All of them are equally likely to give you a maximum idea from a maximum perspective because the function's constant all the time. The likelihood function's constant. But I also have to make my thetas make sense. So I want to try to get as close as I can to what the theta needs to be, so we use the kind of this averaging idea as well as the maximum and the minimum. It's a little bit more complicated, which is why we didn't go through it. But what you can show is that I've got 2 different estimators here for theta. And it's a matter of which one do you want to use based on lots of different ideas. It's the only reason why I'm going through this problem is because it's an idea that's going to pop up later this semester. Not that we're going to actually compute that maximum likelihood estimator. But the idea here is I've got 2 different estimators for theta based on my sample. If you've got 2 different estimators, one of the things that we've worried about for using estimators is bias. Is it biased or unbiased, right? And if it's biased, then you have to adjust for the bias to get an actual estimate. Okay? Another thing that we want to worry about is the variance of an estimator. Because remember, you're going to pick one sample. When you're going to get an estimator, most likely you're going to pick one sample and use that one sample to give you an estimate. Right? You're not going to use several samples typically, especially if you're thinking about this from a manufacturing standpoint. If you're manufacturing an expensive thing and want to test it, are you going to want to do that over and 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 over again? No. Right? So you want to get your best guess at what you can with as little information as possible. Right? So when you're doing these estimators, you're going to make it with as little information as possible. So you're going to take one sample and make your best guess for the estimator based on that sample. Right? Basically at one shot. So you want to make it as good as possible. All right, so if you've got 2 different choices for estimators and one has a higher variance than the other one, even if they have the same expected value, if one has a higher variance than the other one, are you going to use the estimator with the higher variance or the lower variance? Lower, because lower variance means that you should be closer to the middle based on your sample, right? So if you go through the work here, we're not going to, but if you go through the work here, you can show that the variance for the method of moments estimator in this case has a higher variance than the maximum likelihood estimator does. So in practice, if you were going to make a choice between the two, you would pick the maximum likelihood estimator from a variance perspective, because it's more likely to give you a value that's closer to the true value than the method of moments one, because it has a higher variance. Okay? Again, think about this from a practical perspective, right? If you're trying to pick an estimator, you're not going to do it with as little information as possible, especially if you're a manufacturer. Now, if you're doing this from the fact that you've collected a bunch of old data and you let the computer do it, that's fine, right? But if you're going to go out and smash a Porsche, you better get all the information you can from smashing one Porsche, not 1,000 Porsches, right? Right? Okay? So that's the idea behind this. So if you're going to be able to get an estimate, you're going to want to estimate it as close as you can with as little information as possible. So one of the things that we're going to talk about later this semester is finding minimum variance estimators. What estimator can we use that has the smallest possible variance? Yeah, Alex.
So you mentioned that some distributions are prolonged to the method of moments estimator is the same as the maximum likelihood?
Correct. There are a lot to do. Yes.
And in that case, would their variance would be different too?
No.
Okay.
In the other case, they're the same because they're the same estimator.
So where is the uniform one different, or is it?
Oh no, there are other ones that are different. Yeah. The uniforms is about the easiest one to get your mind wrapped around to get at that. But yeah, no, if the method of moments and the maximum likelihood are the same, then yeah, they have the same, because they're the same. I mean, in every respect, they're the same. So. All right. Any other questions about estimators before we go on to confidence intervals? Because that's what we're going to spend the next, I think, 4 sections on. Yeah. It's very exciting. Actually, I think it's maybe even 5. But yeah, Grace.
I don't know how much is finally expected. Or we're supposed to prove that it's not biased.
Mm-hmm.
The expected value of it,
Mhm.
or-
So the expected value of it is what the parameter is supposed to be. Yep. Okay. You sounded very sad about it too.
I don't know how to do it. I forget that, I mean, I looked at it and I was like, yeah.
Okay.
Really sad.
You looked really sad. All right, so let's talk about confidence intervals. All right. So how did the video go?
This is the one that we were supposed to watch last time, right?
Yes, correct. Did you watch it this time, Michael? No, of course you didn't.
I watched it.
There were 10 views this morning when I watched
you
it.
did it.
I didn't remind you.
How many you did?
10?
But there was only 6 when I watched it.
How many people are in the class? 14.
I watched it.
Yeah, I had watched
Wow,
it.
All right, the idea makes sense of what was going on?
I forgot what it was.
Kind of. So it also had to do with, I mean, this idea of the confidence intervals is the same idea as what you just asked me about the problem before, with the, but it's not normal distribution, but the problem before with the S squared being between two things. It's the same concept, trying to find an interval around a parameter that's likely to contain the actual value for the parameter. It's the whole idea, right? So to get to that point, what are we doing? So if we think about the picture, all right, so you've got this parameter that you're trying to estimate for the population, right? Perhaps, okay? So what you're interested in doing, of course, is say you take a sample and you get some sample mean. You want that difference, that distance, to be small, right? We want the distance to be small, but also be likely, right? That's the idea. So if I were trying to find the probability associated with that particular sample mean, you would calculate a z-score as far as means go, correct? For sample means. So from your central limit theorem idea, your z-score would be your x bar minus mu over sigma over the square root of n. That's how we would calculate a z-score according to the central limit theorem. Right? Yep. Okay. So if you just manipulate this and solve for mu instead, you would have what? You would take your z times your sigma over square root of n. Right? And I guess I would have to subtract it on this side, like so. If I were trying to figure out what the mean, if I were just doing this from, if I knew what z was in particular. Right? Now, depending on where this is, this idea here, this is just literally just trying to figure out the mu from this particular z-score. We're thinking about that perspective. But again, we want to do this as being in between a couple of values. So if I want this tail probability here, over here, and then the same idea here. If I want this probability to be small, say alpha, if I want that total probability to be small, we're going to use that symmetry idea to divide the alpha into two pieces. This part will be, oops, this part will be alpha over 2, this part will be alpha over 2, right? So what we want is that the probability, just to write this down, we want the probability that our x bar minus mu over the sigma over square root of n, we want that distance, whatever that probability is we want this to be, say it's less than or equal to some z based on alpha. We want this to be equal to alpha, or sorry, or minus alpha. All right, so let's talk about these different pieces. What does this absolute value piece calculate? The z-score and how far away it is from the actual mean, right? This is giving me limits on how far away I'm allowed to be, right? Right? This is the limits on how far away we're allowed to be from the true mean. That's the idea, right? We want this distance to be big. We want this distance, the probability that this distance is small, to be large. If you think of 1 minus as alpha being, we think about alpha being small, 1 minus alpha is large, relatively speaking, right? Okay. We want the probability that this distance is small to be big. That's what this is saying, right? This is distance, right? Distance is less than or equal to some number. So that's distance is small, right? I'm trying to say it in words rather than math, right? We want the probability that the distance is small, less than or equal to some number, is a large value. So it's likely that the distance is small. It's a predefined where you want that. Your alpha is your predefined probability that you want. So your z sub alpha is based on that predefined probability. We'll talk about how we find it in a second. Let's get it. Good morning.
So is the z equals x minus mu over sigma root n? Is that the distance between x bar and mu?
It would be a signed distance, yes. I didn't put the absolute value on that one.
Oh, okay. So you just got that from the graph?
This or this?
That, sorry.
This is just a z-score. Z-score is distance from mean. It's the distance the sample is from the mean. It's a signed distance, though, because your z could be negative. So that just tells you you're below the mean. Your z, well, distance is probably it's distance relative to spread of the distribution, I should say. Because remember, we're standardizing this by dividing out by the standard deviation, right? Technically, that top part is distance. Because it's just difference between the two, right? If I did absolute value there, that would be distance. But this is kind of relative distance. How bad is the difference based on how spread out the distribution is? Right? If you're 5 apart and you're 5 apart, but your standard deviation is 2, that's pretty far apart. Because that's 2.5 standard deviations away. But if you're 5 apart and your standard deviation is 50, that's close. Because you're 1/10 of the standard deviation away. Say it this way. If my mean is 3, and I get a sample of 8, sample mean of 8, that's a pretty big difference relative to the size, right? But if my mean is 1,000 and I get 1,005, that's not a very big distance relative to the size. I'm ignoring the standard deviation right now, but relative to the size, that's what this whole thing idea here is calculating, is it's distance away based on how spread out the distribution is. So that's why this is a kind of, it's a relative idea. You do relative percentage change kind of things in science, right? This is along those same lines. It's standardizing the distance away it is based on how spread out the distribution is. All right, so this Z sub alpha idea is just, what we're doing here is, I want my X bar to land in this white space. When I take if I take a sample and I calculate the mean, I want it to land in the white space. That's all this statement is saying, graphically. I want it to, because I want it to be close. Yeah, please.
That's kind of where I'm at. Like, well, I'm like, wait, I think you're going to explain it.
Okay.
So, is your confidence interval just going to be the Z sub alpha and negative Z sub alpha?
That's where it's at. That's what we're going to start with, yes.
Start with, or that's what it is?
It's not what it is. It depends on the distribution.
But then if you turn the Z score back into, that's what it is.
That's what it is.
Okay.
Yeah. All right. So this is this part here is representing what my distribution is, right? My underlying whatever the distribution is, right? I'm trying to get a handle on what is that. Okay? That's the whole idea of doing all of this stuff. I want to get a handle on what in the world is the mean of the whole distribution, right? To help me get at what that mean of that whole distribution is, I'm going to go take a sample and calculate its mean instead. Okay? That's what the X bar is representing. If I do this, I want to make sure, I want to hope that this X bar has a really good shot of being close to my mean. Right? If I don't have a really good shot of being close to my mean, then it's useless to me. Right? We agree? If I'm going to use X bar, if I'm going to use the sample mean to estimate the population mean, if I don't have a good shot of the sample mean being close to the population mean, then why am I doing it? Right? I want to have a good shot that my sample mean is going to be close. Okay? So what we're going to do, this alpha is we choose it. We get to choose what the alpha is. Okay? Alpha is a choice. Right? We choose how confident, that's what the alpha means, how confident are we that the X bar, the sample mean, is close to the population mean. That's what the alpha is representing. It's how confident, so the 1 minus alpha is actually how we state that, but that's what the alpha is representing. So if I want to make sure that 95% of the time, I find an interval that should contain my mean, that's a 95% confidence. Okay? Remember again, we don't know, and it's also likely we don't know sigma, but we definitely don't know mu. Right? If we knew mu, why the hell would we be doing samples? Right? Right? Why would I be doing it? If I already know what the population mean is, why would I be taking samples to try to estimate what the population mean is? Right? Yeah, Megan.
How do you know if you're close or not?
That's what the theory is behind this. So the idea is, if we assume we have a normal distribution, then the mean, we already know how to calculate probabilities associated with individual points. Right? So if I want this to be, let's say I have actual honest to goodness numbers. I'm not going to worry about mu right now. Yeah, well, you know what? I'm just going to make it 0. Let's say that this is standard normal. All right, so let's say that this red thing that I've colored in here totals up to 5%, 0.05. Okay, what this, if I take some random, I'll say my x bar here. If I take some random x bar, I know that it doesn't matter what the sample is. I know that the probability that the difference between x bar, oops, I don't need the rate of fraction. I already know this for a fact. With standard normal, I know this for a fact. Oops, I did forget something. Sorry. Forgot my standard deviation on the bottom. I was thinking standard normal and thinking standard deviation was 1, but I forgot to do a sample, so I still need to divide by the square root of it. All right. Why is this true? Okay, let's think about it in terms of I didn't have sample means. The way I was thinking about it to start with. Say that this was just an x, and not an x bar. We would calculate this. Why did I put a mu in there? I don't need a mu, that's a 0. All right, if I do this in general, I don't even, the way I write standard normal, I won't need this mu. All right, if I do this probability, I already know how to calculate probabilities, right? We subtract the mean, we divide by the standard deviation, that gives us a z-score, right? But in general, if I do, no matter what I pick for my x bar, if I do this, and I pick these as my endpoints, then I already know that no matter what I pick for my x bar, this probability is going to be 0.95. Because I've chosen my z's to leave 2.5% on both tails. I've chosen that 1.6 or 1.96 to leave 2.5% on both tails. So I start with the z's that I want to make sure that I've made a range that has a 95% chance of happening, essentially. Yeah, Maureen.
So then, even though like you say like you're 95% confident, you want something lower that's like your boundaries are closer in. Like so you're closer. Or...
So the way you would make these bound, to make these confident, there's a couple of different ways you can make confidence intervals shorter. One is to drop your confidence level. So for example, if I wanted 10% confidence instead of a 90% confidence instead of 95, then you would use 1.645 on both sides, because this would leave 5% on both sides. So if you drop your confidence interval, that'll pull your z-scores in. But now you've only got a 90% chance of pulling out a sample mean that's close, rather than a 95. You've got a smaller interval that's likely to contain the mean, but 10% of the time you're going to be wrong, but based on samples. The other way is to increase your sample size. Because if I increase my sample size, then the denominator is going to get bigger. And so they'll make your difference smaller, relatively speaking. Sam?
What about the speed distribution?
when we do small samples. Same idea, it's just with small samples. Right. So the idea behind constructing these things is to just rearrange, that was what I did in the video, was just rearrange the interval, right? So when you rearrange the interval, that you get the mu that's in between whatever your sample mean is plus that z sub alpha over 2 times sigma over the square root of n, or below. So the idea, again, behind this is, I already know that if I pick my confidence level, I know what the z's are. Right? I know what to use for z. It's plus or minus a value. So for example, if we want a 95% confidence, we're going to use 1.96 and negative 1.96. Because those are the cutoffs where we leave 2.5% above and below. Right? If I want to use 90% confidence, I'll use 1.645 and negative 1.645. Because that leaves 5% above and 5% below. So all we're doing is, what we're saying here is, I know Z to start with. Because I'm picking the confidence level. Okay? I don't know mu, but I do know z. Right? And I'm going to choose a sample so that I can figure out x bar. Right? I want to know, is there a range, rather than an actual value, but is there a range now that's likely to contain the mean based on that sample? That's the whole point of doing this, right? Now, we don't say that there's a 95% chance that the interval we constructed contains the mean. The reason for that is, once we construct an interval, the numbers either are in there or it's not. The population mean doesn't change. So from a probabilistic standpoint, if I give you an interval, it's either in there or it's not, right? The probability is 1 if it's in there, and 0 if it's not. So these probabilities are assigned what's referred to in Latin as a priori, beforehand, before I actually take the sample, okay? If I take a random sample, there's a 95% chance it'll be between these values. That's the idea, okay? But I don't, once I actually compute the sample and get my endpoints, the probability is either 1 or 0 at that point. I know it's a weird interpretation, but that's the idea behind it. All right, so the actual computation of these things is not difficult because that's the formula, okay? And then when you get to an interpretation, what you're saying is you've constructed an interval that should contain the mean, right? More often than not, you're going to construct intervals that will contain the mean. That's what the confidence interval idea is. What we use this for is not, we don't use this to necessarily estimate the mean for purposes of trying to make predictions based on that particular mean. Typically what we use this for is, you've got a manufacturing process that has a, hey, look at that, 2 minutes. We've got a manufacturing process that in the past has created a mean lifetime for the component to last a certain amount of time. Okay? Maybe it's light bulbs, maybe they last 10 months. Okay? Now I've got a new manufacturing process. I've made a better filament for my light bulb. I want to see that I've made an improvement. Okay? So I make these light bulbs, I test them, and I see what the new sample mean is from that test. is it likely that that sample mean, whatever confidence interval I had to start with, is it likely that that sample mean, the confidence interval based on it, would contain the old mean? So, for example, say the old mean was, whatever I said, 10 months. And you, after the change, you've now calculated a confidence interval that's 11 to 13. Do you think you made it better? Do you think you made it better? If you got a confidence interval based on the new sample that's 11 to 13 months, and the old mean was 10, do you think you've made it better based on your information? Yeah, because the new mean is likely between 11 and 13, not 10. Right? That's where we're going with these ideas, with the confidence intervals. It's the fact that if we've changed something, did we make a substantive change? Now, that's not how the problems are going to be phrased as we get to them now, but that's the idea behind this. The old mean was this, we made a change, the new mean's this, by sample. New mean is probably between these two values. Hey, that didn't include the old one. We made a good change. Or maybe you made the change and you got a confidence interval that says 9.5 to 11.5. Yeah, well, now I don't know. It could be 10, because that's in between 9.5 and 11.5, so maybe the change wasn't so good. Maybe we shouldn't go ahead and build this new factory and make all these changes. That's the idea. Okay. All right, we'll do more of this next time. If you haven't watched the video, watch the video. Michael.
I would have just said that.